Imagine for a moment that everything you've ever known about reality is wrong. Not just slightly off, but fundamentally, profoundly incorrect. The solid ground beneath your feet, the air you breathe, the stars scattered across the night sky, even your own body, all of it, everything that seems so concrete and real, is nothing more than an elaborate cosmic symphony played out on strings so impossibly tiny that they make an atom look like a galaxy. This isn't science fiction. This isn't philosophical musing. This is string theory, and it might just be the closest thing we have to understanding the true nature of everything that exists. Picture this. Right now, as you listen to these words, you exist in more dimensions than you can perceive. Hidden dimensions, curled up so small that they're tucked away in every point of space around you. Dimensions that vibrate with energies that give rise to every force, every particle, every phenomenon in the universe. You could be standing in a room right now, but that room contains infinite complexity you cannot see, cannot touch, cannot experience with your ordinary senses. How does that make you feel? Does it fill you with wonder? With dread? With the uncomfortable sensation that you're only seeing the shadow of reality, like prisoners in Plato's cave? Let me ask you something. What are you made of? You might say cells. Go deeper. Molecules. Deeper still. Atoms. And inside those atoms, protons, neutrons, electrons. But what are those made of? Quarks and leptons, the fundamental particles. But here's where it gets strange, where the comfortable world of classical physics breaks down and we tumble into something far more bizarre. What are those fundamental particles made of? For decades, physicists told us they were points, mathematical dots with no size, no structure, just pure properties like mass and charge existing at a single location in space. But that answer created more problems than it solved. Problems so severe they threatened to tear apart our entire understanding of how the universe works. In the late 1960s, a young physicist named Gabriele Veneziano was wrestling with a problem that had stumped the greatest minds in physics. He was trying to understand the strong nuclear force, the mysterious power that holds atomic nuclei together against the electromagnetic repulsion of positively charged protons trying to fly apart. The mathematics refused to cooperate. The numbers didn't make sense. Then, almost by accident, he stumbled upon an elegant mathematical function, something called the Euler beta function, discovered 2 centuries earlier by the mathematician Leonhard Euler. This function, created for entirely different purposes, somehow perfectly described the behavior of these particles. But why? What was it about this particular equation that captured something true about reality? It took years before physicists realized what Veneziano had actually discovered. The beta function that described these particles so well was the same mathematics that would describe tiny, vibrating strings. Not strings like guitar strings or violin strings, though the metaphor is apartment. These would be strings existing at the Planck length, a scale so monumentally small that if you enlarged a string to the size of a tree, an atom would be as large as the entire observable universe. At this scale, reality becomes something entirely alien to our everyday experience. Think about a violin string for a moment. When you pluck it, it vibrates at different frequencies. Each frequency produces a different note. The same string can create an A, AB, AC, depending on how it vibrates. Now, transport that concept into the quantum realm. Imagine that every fundamental particle in existence, every electron, every quark, every photon, every neutrino, isn't actually a particle at all, but rather a tiny loop of string vibrating at a specific frequency. An electron is just a string vibrating one way. A quark is the same string vibrating differently. All matter, all energy, all forces, they're all the same fundamental object, just playing different notes in the cosmic symphony. It's beautiful, elegant, almost poetic. But is it true? Here's where string theory becomes more than just an interesting mathematical curiosity. It does something that no other theory in physics has ever managed to do. It unifies. For nearly a century, physics has been split down the middle. torn between two incredibly successful but fundamentally incompatible descriptions of reality. On one side, you have General Relativity, Einstein's masterpiece, which describes gravity as the curvature of space-time itself, works beautifully at large scales, governing planets, stars, galaxies, the entire cosmos. On the other side stands quantum mechanics, the strange probabilistic theory that describes the behavior of particles at the smallest scales, a theory so bizarre that even its founders never fully accepted its implications. Both theories work spectacularly well in their own domains. General relativity predicted black holes, gravitational waves, the expansion of the universe, all confirmed by observation. Quantum mechanics gave us transistors, lasers, nuclear power, and explains the behavior of atoms and subatomic particles with astounding precision. But when you try to combine them, when you try to describe gravity at quantum scales, the mathematics explodes. You get infinities, meaningless answers, a complete breakdown of predictability. It's as if the universe speaks two different languages, and we're the confused translators trying to make sense of the contradiction. Imagine trying to understand a book where the first half is written in English and the second half in Chinese, but you only know one language. That's been the state of physics for generations. We have two books describing reality, and they refuse to tell the same story. String theory promises to be the Rosetta Stone, the key that translates both languages into a single, coherent narrative. When physicists applied string theory to the problem of quantum gravity, something miraculous happened. The infinities disappeared. The mathematics became finite, calculable, meaningful. For the first time, gravity and quantum mechanics spoke the same language. But this unification came with a price so strange that many physicists still struggle to accept it. The mathematics of string theory only works in a universe with more than the 3 dimensions of space and 1 dimension of time that we experience. Depending on which version of string theory you're working with, you need 10 dimensions, or even 11. 10 or 11 dimensions. Let that sink in for a moment. Where are these extra dimensions? Why can't we see them? Why don't we fall off into some hidden direction when we walk down the street? The answer, according to string theory, is that these extra dimensions are compactified, curled up so incredibly small that they exist at every point in space but remain invisible to us. Imagine an ant walking on a tightrope suspended high above a canyon. To the ant, the rope might seem like a one-dimensional line, stretching forward and backward. But if the ant looks more carefully, it realizes the rope has thickness, a circular dimension wrapped around the length. The ant can walk forward and backward on the rope, but it can also walk around the rope's circumference. Now imagine that circular dimension shrank down to microscopic size. From far away, the rope would look like a simple line again, even though that extra dimension still exists, just too small to see from a distance. That's what string theory suggests about our universe. At every point in the 3-dimensional space we inhabit, there are 6 or 7 additional dimensions, curled up into complex geometric shapes called Calabi-Yau manifolds. These aren't simple circles like our rope analogy. They're elaborate, beautiful, mind-bendingly complex structures with their own topology, their own geometry. And here's the truly remarkable part. The exact shape of these hidden dimensions determines the properties of the particles we observe. The masses of electrons and quarks, the strengths of the fundamental forces, all of it emerges from the geometry of these compactified dimensions. Reality itself is geometry. Can you picture it? Right now, wherever you are, your hand exists in 3 dimensions you can see, but it also extends into 6 dimensions you cannot perceive, dimensions that are curved and twisted in ways that give rise to every property of every atom in your body. It's like discovering that a painting you've admired your whole life has layers upon layers of depth that were invisible until you put on special glasses. Does this thought comfort you or unsettle you? What does it mean for your sense of place in the universe to realize you're immersed in dimensions you cannot experience? But wait, because string theory gets stranger still. In the 1980s and early 90s, as physicists explored the mathematical landscape of string theory, they discovered not 1 but 5 different versions. Each version had its own mathematical structure, its own rules, its own way of describing reality. This was embarrassing. String theory was supposed to be the theory of everything, the ultimate description of reality. How could there be 5 different theories of everything? Which one was correct? Or were all of them wrong? Then, in the mid-1990s, a physicist named Edward Witten made a discovery that changed everything. Through a series of brilliant insights, Witten showed that these 5 seemingly different theories were actually 5 different perspectives on a single, deeper theory. It's like looking at a cube from different angles. From one side you see a square. From another angle you see a different square. From a corner you see a hexagon. Same object, different views. Witten proposed that there was one master theory underlying all 5 string theories, and he called it M-theory. What does the M stand for? Witten has never definitively said. Mother theory, master theory, membrane theory, mystery theory, magic theory. The ambiguity seems almost intentional, a reminder that we're dealing with something profound that we don't yet fully understand. M-theory suggests that the fundamental objects aren't just one-dimensional strings, but can be zero-dimensional points, two-dimensional membranes, three-dimensional blobs, and even higher-dimensional objects called brains. Our entire universe might be a three-dimensional brain floating in a higher-dimensional space. Think about that. Everything you've ever known, every star in the sky, every galaxy, every planet, all of it could be confined to a three-dimensional membrane embedded in a space with more dimensions. It's like we're living on the surface of a cosmic bubble, and there might be other bubbles, other brains, other universes floating nearby in the higher dimensional space. Could these other brains interact with ours? Could they collide? Some physicists have speculated that the Big Bang itself might have been the result of 2 brains colliding in higher dimensional space. Your existence, the existence of stars and planets and life, all of it the aftershock of a collision in dimensions we cannot perceive. Let me paint you a picture of what the early universe might have looked like through the lens of string theory. Imagine going back in time, watching the universe contract, watching stars compress into clouds of gas, watching atoms break apart into their constituent particles. Keep going back. The universe becomes smaller, denser, hotter. You approach the Big Bang, that moment 13.8 billion years ago when everything began. In conventional physics, as you get closer to time zero, the mathematics breaks down. Densities become infinite. Temperatures become infinite. The equations stop making sense. But in string theory, something different happens. Because strings have a finite size, even if that size is impossibly small, they can't be compressed to a point. There's a limit to how small, how dense, how hot things can get. The fabric of space-time itself becomes grainy at the Planck scale, like a photograph that reveals its pixels when you zoom in far enough. Some versions of string theory suggest that the Big Bang wasn't the beginning at all, but a transition, a moment when a previous phase of the universe transformed into what we see today. Perhaps the universe has existed eternally, cycling through phases of expansion and contraction, bouncing rather than beginning. Perhaps time itself has no beginning, stretching infinitely into the past. How does that make you feel, the idea that the universe might be eternal? Does it fill you with awe, with vertigo? For all of human history, we've asked where we came from, why there's something rather than nothing. String theory suggests the question itself might be based on a false assumption that there was never nothing, that existence is the default state and has always been. Now, I need to be honest with you about something. Everything I've described so far, as beautiful and elegant as it sounds, remains unproven. String theory makes predictions, but most of them involve energies and scales far beyond what we can currently test in experiments. To directly observe a string, you'd need a particle accelerator as large as the galaxy. To see the extra dimensions, you'd need to probe distances a billion times smaller than anything we can currently measure. This is one of the central criticisms of string theory, and it's a valid one. Science progresses through a cycle of theory and experiment. You make a prediction, you test it, you confirm or refute the theory. But what happens when a theory makes predictions that are, for all practical purposes, untestable? Does it remain science, or does it become philosophy, mathematics, sophisticated speculation? This question haunts string theory and divides the physics community. Some see it as the future of physics, the only framework that has any hope of unifying our understanding of nature. Others see it as a dead end, a beautiful mathematical structure that might have nothing to do with reality. One of the most vocal critics has been physicist Lee Smolin, who argues that string theory has consumed the careers of the brightest minds in physics for decades without producing testable predictions or experimental confirmations. He points out that the theory has become so flexible, with so many possible versions depending on how the extra dimensions are compactified, that it can be adjusted to match almost any experimental result. A theory that can explain anything, he argues, actually explains nothing. It becomes unfalsifiable, and unfalsifiable theories aren't science. Other critics, like Peter Woit, have pointed out that string theory requires extraordinary fine-tuning. The values of various parameters in the theory need to be set to incredibly specific values for the theory to produce a universe that looks anything like ours. Why those values and not others? The theory doesn't say. It's like finding a radio perfectly tuned to your favorite station and being told that's just how it happened to be set, with no explanation for why. But here's the thing that defenders of string theory point out: we don't have a better alternative. Every other attempt to unify gravity with quantum mechanics has failed. Loop quantum gravity, another approach to quantum gravity, has its own problems and limitations. The standard model of particle physics, our best description of the fundamental particles and forces, works beautifully but is obviously incomplete. It doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't explain why the particles have the masses they do or why there are 3 generations of matter. It's a framework full of holes, parameters that have to be measured rather than predicted, mysteries that demand explanation. String theory, at least in principle, explains all of it. If we could solve the theory completely, if we could determine the exact shape of the compactified dimensions, string theory would tell us the masses of all particles, the strengths of all forces, why the universe has the properties it does. It would be the ultimate answer, the final theory, the end of physics as a search for more fundamental laws. Everything else would just be working out the details. Let me take you deeper into one of the strangest predictions of string theory: supersymmetry. The theory requires that every particle we know has a partner particle, a superpartner, with different properties. Every matter particle has a force-carrying superpartner. Every force-carrying particle has a matter superpartner. Electrons have selectrons. Quarks have squarks. Photons have photinos. It sounds like science fiction, like someone just added a silly prefix to particle names. But supersymmetry solves real problems in physics. For one, it stabilizes the mass of the Higgs boson. In the standard model without supersymmetry, quantum corrections should make the Higgs particle impossibly heavy, so heavy it would destabilize the entire universe. The fact that the Higgs has the mass it does, about 125 times the mass of a proton, requires incredible fine-tuning unless something cancels out those quantum corrections. Supersymmetry provides that cancellation. The contributions from particles and their superpartners exactly balance out, naturally explaining why the Higgs mass is what it is. Supersymmetry also provides a candidate for dark matter. Astronomical observations tell us that most of the matter in the universe is invisible, interacting with normal matter only through gravity. Galaxies rotate too fast. Galaxy clusters are too massive. The universe expands in a way that requires matter we can't see. The lightest supersymmetric particle would be stable, neutral, and would interact only weakly with normal matter, exactly the properties we need for dark matter. If supersymmetry is real, we're swimming in a sea of these particles right now, billions of them passing through your body every second, ghosting through the Earth without interaction. Physicists have been searching for signs of supersymmetry for decades. The Large Hadron Collider, the massive particle accelerator straddling the border between France and Switzerland, was supposed to discover superpartners. It found the Higgs boson in 2012, a triumph of physics. But so far, no superpartners. Does this mean supersymmetry is wrong? Not necessarily. It might just mean the superpartners are heavier than we expected, beyond the energy range the LHC can probe. Or it might mean that string theory's prediction of supersymmetry is wrong, or that supersymmetry exists but in a form different than string theory requires. This is the frustrating and fascinating position string theory occupies. It makes predictions, but they're predictions for energy scales just beyond our reach, or for phenomena so subtle we haven't figured out how to measure them yet. It's like being told there's treasure buried in your backyard, somewhere between 6 feet and 6 miles deep. The treasure might be real, but you might never have the tools to dig it up. Yet despite these challenges, string theory has contributed enormously to physics and mathematics. The mathematics of string theory is stunningly rich, revealing connections between different areas of mathematics that no one suspected existed. Mirror symmetry, a property of certain Calabi-Yau manifolds, has led to breakthroughs in pure mathematics, allowing mathematicians to solve problems that had been unsolved for decades. The AD-SCFT correspondence, a conjecture emerging from string theory, suggests a deep connection between gravity in certain curved spaces and quantum field theories without gravity in one fewer dimension. This holographic principle has applications far beyond string theory, influencing how physicists think about black holes, quantum entanglement, and the nature of spacetime itself. Think about the implications of holography for a moment. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space, like a three-dimensional image encoded on a two-dimensional hologram. Your entire room, with all its depth and volume, could in principle be completely described by information encoded on the walls, floor, and ceiling. You, with all your complexity, your thoughts, your memories, your consciousness, might be equivalent to information patterns on a lower dimensional boundary somewhere. Some physicists have taken this idea even further, speculating that our entire universe might be a hologram, a projection from information encoded on a distant boundary billions of light years away. In this view, the three-dimensional space you experience is an illusion, a convenient way for the universe to organize information that's actually stored elsewhere, in fewer dimensions. It's reminiscent of Plato's cave allegory, the idea that what we perceive is just a shadow of a deeper reality. But here, the suggestion isn't philosophical, it's mathematical, emerging from the equations of string theory and quantum gravity. Does this bother you? The idea that you might be a projection, a hologram, information without the substance you feel yourself to have? Or is it just another way of describing the same reality, no more or less real than the particle description or the wave description or the string description? These are questions that physics raises but cannot answer, questions that spill over into philosophy, into metaphysics, into the fundamental problem of what we mean by real. Let's talk about what would happen if string theory is correct. What would it mean for humanity, for our understanding of our place in the cosmos? First and most profoundly, it would mean that reductionism wins. The ancient dream of explaining the complex in terms of the simple, of finding the basic building blocks from which everything else emerges, would be realized. Not atoms, not particles, but strings and brains, vibrating in higher dimensions according to elegant mathematical laws. Everything else, chemistry, biology, psychology, sociology, all of it would in principle be reducible to the behavior of strings. But here's the paradox. Even if string theory is correct and we knew all the laws perfectly, we still couldn't predict most of the things we care about. The behavior of strings gives rise to particles. Particles give rise to atoms. Atoms give rise to molecules. Molecules give rise to cells. Cells give rise to organisms. Organisms give rise to ecosystems, societies, cultures, thoughts, emotions, art, love, consciousness. At each level, new properties emerge that aren't obvious from the level below. You can't look at a quark and predict Shakespeare. You can't look at a string vibration and predict a sunset or a symphony or the feeling you get when you laugh with old friends. So even in a universe completely described by string theory, there would still be mystery, still be wonder, still be things that surprise us and move us and make us feel alive. The theory of everything wouldn't be the end of discovery, just the end of one particular kind of discovery, the search for more fundamental laws. Everything else, the entire rich complexity of existence, would still be there waiting to be explored. Some physicists worry about this, actually. They worry that if string theory is proven correct, if we reach the bottom level of reality and find the final laws, physics as a field will end. There will be nothing left to discover at the fundamental level. But I think this worry misunderstands what science is about. Science isn't just about finding fundamental laws. It's about understanding how the universe works at every level, from strings to societies. Even with a complete theory of the fundamental, we'd have centuries of work understanding how complexity emerges, how the simple gives rise to the intricate. Now let me tell you about one of the strangest ideas to emerge from string theory: the landscape problem. Remember how I said the extra dimensions could be curled up in different ways? Turns out there are a lot of different ways. Not dozens, not thousands. The number of possible configurations, the number of different Calabi-Yau manifolds that could serve as the hidden dimensions, is estimated to be around 10 to the power of 500. That's a 1 followed by 500 zeros, a number so large it beggars comprehension. To put that in perspective, the number of atoms in the observable universe is around 10 to the power of 80. The number of possible string theory vacua, different configurations of the compactified dimensions, is unimaginably larger. Each configuration would give rise to a universe with different physical laws, different particles, different forces. In one configuration, electrons might be heavier. In another, gravity might be stronger. In another, there might be 5 fundamental forces instead of 4. This is the string theory landscape, and it represents either a crisis or an opportunity, depending on your perspective. The crisis is that with 10 to the 500 possible universes, how do we explain why we live in this one? Why do the particles have the masses they do? Why are the forces as strong as they are? String theory doesn't predict a unique answer. It predicts 10 to the 500 answers, and we have to look around at our universe and figure out which one we're in. Some physicists see this as a failure. A true theory of everything should predict unique values for all the constants of nature, explaining why the universe is the way it is because it couldn't be any other way. Instead, string theory seems to say the universe could be 10 to the 500 different ways, and ours is just one possibility among an inconceivable multitude. But other physicists see opportunity. They point out that our universe seems fine-tuned for life in ways that have puzzled scientists for decades. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the electromagnetic force were slightly different, atoms wouldn't form. If the strong nuclear force were slightly weaker, only hydrogen would exist. The values of the fundamental constants seem precisely calibrated to allow for complexity, for chemistry, for life. Why? In a universe with unique laws, this fine-tuning is mysterious, even suspicious. Some see it as evidence for a designer, a cosmic engineer who set the parameters just right. But the string theory landscape offers a different explanation: the anthropic principle. If there are 10 to the 500 different possible universes, perhaps all of them actually exist somewhere, somewhen. Perhaps there's a multiverse, a vast ensemble of universes with every possible configuration of the compactified dimensions. In most of these universes, the constants are wrong for life. Stars don't form, or they burn too hot, or atoms don't exist, or chemistry doesn't work. But in a tiny fraction of universes, the constants are just right, and in those universes, life can arise, intelligence can evolve, physicists can exist to ask why the constants have the values they do. We find ourselves in a life-friendly universe not because the universe was designed for life, but because we couldn't exist in any other kind of universe to ask the question. It's selection bias on a cosmic scale. This is the anthropic explanation, and it's deeply controversial. Some physicists find it elegant and explanatory. Others find it a cop-out, an abandonment of the scientific quest to explain why things are the way they are. Let me ask you, how do you feel about the multiverse? Does it make you feel insignificant, knowing that our universe might be just one of 10 to the 500, that everything you've ever known or cared about exists in just one tiny corner of a vastly larger reality? Or does it fill you with wonder, with the staggering realization that existence is far richer and stranger than we ever imagined? There's another aspect of string theory I need to tell you about, something that might be its most radical claim. In string theory, space-time itself isn't fundamental. The dimensions we experience, the stage on which the cosmic play unfolds, emerge from something deeper. Strings and branes interact in ways that give rise to the appearance of space, the appearance of time, the appearance of geometry. But at the deepest level, reality might be something else entirely, something we don't have words for, something our minds might not be equipped to understand. Think about what this means. You experience yourself as existing in space, persisting through time. But string theory suggests that space and time are emergent properties, like temperature or pressure, things that appear at large scales but dissolve into something else when you look closely enough. Just as temperature is really just the average motion of molecules, space-time might be a large-scale approximation of something more fundamental happening with strings and quantum information. What is that more fundamental something? We don't know. Some physicists talk about quantum entanglement, the mysterious connection between particles that seems to transcend space. Others talk about information, suggesting that reality is fundamentally about relationships and correlations rather than objects existing in a container called space. It's speculative, cutting edge, the kind of idea that might seem absurd in retrospect or might be the seed of the next revolution in physics. Let's ground ourselves for a moment in some of the concrete successes of string theory. Beyond the mathematical contributions and the conceptual frameworks, has string theory made any testable predictions? The honest answer is, maybe, but we're not sure yet. String theory generically predicts the existence of gravitons, particles that carry the gravitational force, just as photons carry the electromagnetic force. But gravitons would be incredibly difficult to detect, interacting so weakly with matter that we may never be able to build a detector sensitive enough to spot them. String theory also makes predictions about the cosmic microwave background, the faint glow of radiation left over from the Big Bang. Certain patterns in this radiation could serve as signatures of string theory, fingerprints of the extra dimensions or of cosmic strings, one-dimensional defects in space-time that might have formed in the early universe. Astronomers have searched for these signatures. So far, the results are inconclusive, neither confirming nor ruling out string theory. There's also the possibility that the LHC or future particle accelerators might see something unexpected, some deviation from the standard model that points towards string theory. Maybe microscopic black holes forming in particle collisions, a possibility if the extra dimensions are larger than the minimum size. Maybe missing energy carried off by particles escaping into the extra dimensions. So far, nothing. But the absence of evidence isn't evidence of absence, at least not yet. Here's a question for you to ponder. What would you do if you were a young physicist today, faced with the choice of working on string theory or something else? Would you dedicate your career to a theory that might be correct but untestable, knowing you could spend your entire professional life on something that never receives experimental confirmation? Or would you work on more experimentally accessible problems, even if they're less fundamental, less ambitious? There's no right answer. Some of the greatest physicists of recent generations have made different choices, and both paths have led to valuable contributions. The human side of string theory is fascinating and sometimes troubling. In the 1980s and 90s, string theory became so dominant in theoretical physics that it was difficult to get an academic job if you weren't working on it. Departments wanted string theorists. Grant agencies funded string theory research. Students saw where the opportunities were and flocked to the field. This created a kind of intellectual monoculture, where other approaches to fundamental physics were marginalized, where brilliant physicists struggled to find positions because they were working on the wrong problems. Some people who lived through this era describe it as exciting, a gold rush atmosphere where new discoveries emerged every month. Others describe it as stifling, a period when alternative ideas couldn't get a hearing because everyone had drunk the string theory Kool-Aid. The truth, as always, is probably somewhere in between, and probably different for different people in different departments at different institutions. But it raises important questions about how science works as a social enterprise. Science isn't just about individual genius having insights. It's about communities of researchers building on each other's work, critiquing each other's ideas, allocating limited resources to different research programs. When one theory becomes dominant, there's a risk of groupthink, of missing alternatives, of investing too much in an approach that might be wrong. But there's also the benefit of concentrated effort, of many minds attacking the same problem from different angles, of building a deep and sophisticated understanding of one approach. Where does string theory stand today, in the early 21st century? It's no longer the only game in town. Loop quantum gravity has developed into a sophisticated research program with its own insights and predictions. Other approaches, like causal set theory and emergent gravity, are being explored. String theory remains one of the most active areas of research in theoretical physics, but it's no longer the overwhelming focus it once was. There's more diversity, more pluralism, which most physicists see as healthy. At the same time, string theory has matured. The wild optimism of the 1980s, when some physicists thought a final theory might be just around the corner, has given way to a more measured assessment. Most string theorists today acknowledge that they're working on a long-term research program that might take decades or even centuries to fully develop and test. They emphasize the mathematical insights and conceptual clarifications the theory provides, even in the absence of experimental confirmation. Interestingly, string theory has found unexpected applications far from fundamental physics. The mathematics of string theory turns out to be useful for describing certain condensed matter systems, materials with exotic properties like high-temperature superconductivity. It's been used in nuclear physics to model the quark-gluon plasma created in heavy ion collisions. The holographic principle derived from string theory has been applied to problems in quantum information theory. So even if string theory turns out to be wrong as a description of fundamental reality, it's already proven its value as a theoretical tool. Let me tell you about one of the most mind-bending aspects of string theory: black holes. In general relativity, a black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. The mathematics predicts a singularity at the center, a point where density becomes infinite and the laws of physics break down. For decades, this singularity was seen as a problem, a sign that general relativity was incomplete. In the 1970s, Stephen Hawking made an astonishing discovery using quantum mechanics. He showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon, slowly evaporating over time. A black hole has a temperature. It radiates like a hot object. This was revolutionary, linking gravity, quantum mechanics, and thermodynamics in unexpected ways. But Hawking's discovery created a new problem: the black hole information paradox. When matter falls into a black hole, it carries information, the quantum state of all the particles. If the black hole then evaporates into thermal radiation, what happens to that information? Hawking argued it's destroyed, lost forever. But this violates a fundamental principle of quantum mechanics. Information is never destroyed, only transformed. String theory offers a resolution. Using the mathematics of string theory, physicists have been able to calculate the entropy of certain black holes, counting the number of quantum states, and getting exactly the answer predicted by Hawking's semi-classical calculations. This was a triumph, showing that string theory could reproduce results from quantum field theory and general relativity while providing a deeper understanding of what's going on. More recently, string theorists have argued that information isn't lost in black holes. It's scrambled in incredibly complex ways, but it's eventually released in the Hawking radiation through subtle quantum correlations. The information is preserved, quantum mechanics is upheld, and black holes become laboratories for testing ideas about quantum gravity, even if we can't build actual black holes to experiment on. Imagine standing at the event horizon of a black hole. In general relativity, the horizon is a smooth, featureless surface. You could cross it without noticing, though you'd be doomed to fall toward the singularity at the center. But in string theory, the horizon might be something altogether different. Some calculations suggest it could be a chaotic, roiling surface of strings and brains, a firewall that would incinerate anything trying to cross. This is the black hole firewall paradox, a current debate in theoretical physics that gets at deep questions about the nature of space-time and quantum mechanics. These aren't just abstract puzzles. They're windows into how reality works at the most extreme conditions. Conditions where our everyday intuitions completely fail. The fact that string theory has something to say about these puzzles, even if we're not sure if what it says is correct, demonstrates its power as a theoretical framework. Now let's talk about time. You experience time as flowing, as carrying you from past through present toward future. But what is time, really? In Newton's physics, time was absolute, ticking away uniformly throughout the universe. Einstein showed this was wrong. Time is relative, flowing at different rates depending on how fast you're moving and how deep you are in a gravitational field. Time is part of the fabric of space-time, inseparable from space itself. But in string theory, time might be even stranger. Some versions of the theory suggest that time, like space, could have multiple dimensions. Imagine not one future but a plane of futures, or a volume of futures, branching in directions you can't perceive. Other versions suggest that time might be circular at the quantum level, looping back on itself in Planck scale cycles. There's also the possibility that time is emergent, not fundamental. Just as the flow of heat from hot to cold emerges from the statistical behavior of molecules, the flow of time from past to future might emerge from deeper, timeless laws governing strings and quantum information. In this view, the universe at its deepest level is timeless, eternal, and the sense of change, of causation, of before and after, is an approximation that appears at large scales. How does this make you feel? Does it comfort you to think that time might be an illusion, that past and future might coexist in some eternal now? Or does it disturb you, undermining your sense of free will, of making choices that shape the future? These are questions that physics raises but doesn't answer, questions that each of us has to grapple with in our own way. Let's explore what string theory says about the beginning of the universe in more detail. The conventional Big Bang model says the universe began in a state of infinite density and temperature 13.8 billion years ago. But infinity is a red flag in physics, usually a sign that your theory has broken down, that you're extrapolating beyond where your equations are valid. String theory avoids this infinity. Because strings have a minimum length, density can't become infinite. Some string theorists have proposed scenarios where our universe emerged from a collision of brains in higher dimensional space. Others suggest a cyclic universe, eternally expanding and contracting. Still others propose that the Big Bang was a transition from a previous phase, perhaps a quantum vacuum state that decayed into the hot, dense early universe. There's a particularly intriguing idea called the ekpyrotic universe. In this scenario, our three-dimensional brain floats in a higher dimensional space parallel to another brain. Every trillion years or so, the brains collide, and each collision produces what we would perceive as a Big Bang from inside one of the brains. The matter and energy in our universe are the debris from the most recent collision. This would mean the Big Bang wasn't the beginning of time, just the beginning of this phase, this era. Before our Big Bang, there were others. After our universe grows cold and empty in the far future, there will be another collision, another Big Bang, another universe. It's a cosmological model that's simultaneously humbling and awe-inspiring. Humbling because it suggests our universe, with all its galaxies and stars and planets, is just one event in an eternal cycle. awe-inspiring because it paints a picture of existence as fundamentally creative, endlessly renewing itself, never running down into final heat death but always regenerating. These ideas are speculative. I need to emphasize that. We don't have direct evidence for brane collisions or cyclic universes, but they're taken seriously by physicists because they emerge from the mathematics of string theory and M-theory, and because they make predictions that could, in principle, be tested by astronomical observations of the cosmic microwave background or the distribution of galaxies. One question that string theory raises is whether the laws of physics could have been different. In our universe, electrons have a certain mass, the speed of light has a certain value, gravity has a certain strength. But are these the only possible values? Could there be universes where electrons are heavier or lighter, where light travels faster or slower, where gravity is stronger or weaker? Before string theory, many physicists assumed that a final theory would uniquely predict the laws of physics. There would be one set of equations, one solution, one universe. But the string theory landscape suggests otherwise. The laws of physics might be contingent, depending on which vacuum state the universe is in, which configuration of the compactified dimensions was selected. This has profound philosophical implications. It means the laws of physics aren't necessary truths, eternal and unchanging. They're more like facts about our particular universe, no more fundamental than the fact that Earth has one moon or that water freezes at 0 degrees Celsius. In other universes with other vacuum states, the laws would be different. Some physicists find this depressing, a retreat from the goal of explaining why the universe is the way it is. Others find it liberating, a recognition that contingency and specificity are built into the fabric of reality. The universe doesn't have to justify itself to us. It doesn't have to satisfy our aesthetic desire for unique, elegant explanations. It just is the way it is, and we're here to observe it because we couldn't exist in universes with different laws. Let me ask you something personal. Do you think the universe has a purpose? String theory doesn't answer this question, can't answer it, because purpose isn't a scientific concept. But it changes the context in which we ask. If there are 10 to the 500 universes in the landscape, or infinitely many universes in an eternal multiverse, then any particular universe doesn't need a purpose. It's just one possibility among many, existing not for any reason but simply because it can. Yet even if the universe as a whole has no purpose, your life can still have meaning. Purpose and meaning are things we create, not things we discover encoded in the fundamental laws. You can look at the universe described by string theory, vast and strange and indifferent, and still decide to love, to create, to explore, to make your corner of existence a little better. The absence of cosmic purpose doesn't imply the absence of human meaning. Let's talk about consciousness for a moment. String theory, like all of physics, describes matter and energy, particles and forces, fields and spacetime. It doesn't have anything obvious to say about consciousness, about the subjective experience of what it's like to be you. This is sometimes called the hard problem of consciousness, and it's a problem that physics has largely ignored. But there are interesting questions at the intersection. If string theory is correct and all matter emerges from vibrating strings, then your brain, the physical organ that somehow gives rise to consciousness, is made of strings. Your thoughts, your emotions, your sense of self, all of it is somehow the result of unimaginably complex patterns of string vibrations. Every time you have a thought, strings in your neurons vibrate in new patterns. Every memory you form is encoded in string configurations. Does this reduce consciousness to physics? Or does it point to something mysterious about strings, some property we don't yet understand that allows them to generate subjective experience when arranged in the right configurations? We don't know. String theory doesn't tell us, but it's worth pondering. If the theory of everything explains everything physical, does consciousness count as physical? And if not, what does that say about the completeness of the theory of everything? Some philosophers and physicists have speculated that consciousness might be a fundamental feature of reality, like mass or charge, something that exists at the level of strings or even deeper. This is panpsychism, the idea that everything has some form of experience, however rudimentary. A string might have some infinitesimal glimmer of awareness. Complex arrangements of strings, like brains, would have more complex awareness. This is highly speculative, far beyond anything string theory actually says, but it's an example of how a theory of physics can inspire philosophical reflection. Here's another question to ponder. If string theory is correct and our universe has 10 or 11 dimensions, could there be creatures that experience more dimensions than we do? Just as we're blind to 6 or 7 compactified dimensions, could there be beings whose perceptual apparatus allows them to see those dimensions, to move through them, to manipulate them? To us, such beings would seem to have impossible powers, appearing and disappearing at will, reaching inside closed containers, perhaps even accessing different points in time. They would be like gods from our perspective, but they would simply be organisms evolved to perceive more of reality than we can. This is pure speculation, of course. There's no evidence for higher dimensional beings. But string theory at least makes the speculation coherent. It provides a framework where such beings could exist without violating the laws of physics. Whether they actually do exist is another question entirely. Let me tell you about one of the most exciting recent developments in string theory: the connection to quantum entanglement. Entanglement is a phenomenon where two particles become correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein famously called it spooky action at a distance and thought it showed that quantum mechanics was incomplete. But experiments have confirmed that entanglement is real. In the last decade, string theorists have discovered that entanglement might be even more fundamental than we thought. Using the ASLEEP correspondence, they've shown that in certain models, the geometry of spacetime itself is built from quantum entanglement. Particles that are entangled are connected by wormholes, shortcuts through spacetime. The more entanglement, the more spacetime. If entanglement is broken, spacetime tears apart. This is the ER equals EPR conjecture, proposed by Juan Meldacena and Leonard Susskind. ER refers to Einstein-Rosen bridges, another name for wormholes. EPR refers to the Einstein-Podolsky-Rosen paper on entanglement. The idea is that these two seemingly different phenomena are actually the same thing viewed from different perspectives. Every entangled pair is connected by a wormhole. If this is true, and it's still very much a conjecture being explored, it would mean that spacetime emerges from entanglement. The fabric of reality is woven from quantum correlations. Distance, locality, the entire structure of space, it's all built from something more fundamental: information and entanglement. Think about what this means for the question of what's real. You experience yourself as separate from the person sitting next to you, separated by space. But if space itself emerges from entanglement, and particles in your body are entangled with particles elsewhere, then in some deep sense you're not as separate as you seem. The universe is a unified whole, and the appearance of separation is an emergent property, real at the level of everyday experience, but dissolving into connection at the fundamental level. Does this resonate with you? Many spiritual and philosophical traditions have taught that separation is an illusion, that we're all connected, that the universe is one. String theory and quantum mechanics don't prove these ideas, but they do suggest that the physics of the universe is stranger and more holistic than common sense suggests. Let's return to the question of testability. I've mentioned that string theory is hard to test because it makes predictions at energy scales far beyond current experiments. But there's a subtler form of testing: mathematical consistency. A theory that's mathematically inconsistent, that leads to contradictions, is definitely wrong. String theory is remarkably consistent. Every time physicists have probed it, expecting to find contradictions, the theory has held together. Anomalies that would destroy other theories cancel out in string theory. This doesn't prove it's correct, but it's a good sign. There's also something called the swampland program, a recent development in string theory that aims to identify which effective field theories can be consistently embedded in string theory and which can't. The idea is that the space of all possible quantum field theories is divided into the landscape, theories that can come from string theory, and the swampland, theories that can't. By identifying features that characterize swampland theories, physicists can make predictions. If we observe a field theory with swampland features, string theory is wrong. This is an exciting development because it offers a path toward falsifiability. The program is still young, but it's already made some interesting predictions about cosmology and particle physics. Time will tell if these predictions pan out or if observations push us away from string theory. Let me paint you a picture of what the future might hold if string theory is correct. Imagine a civilization millions of years more advanced than ours, with technology we can barely conceive. They've mastered the extra dimensions, learned to manipulate the compactified spaces at every point. They can adjust the values of the fundamental constants in small regions, creating zones where gravity is weaker or electromagnetism stronger. They use cosmic strings as energy sources, tapping the tension in these one-dimensional defects in space-time. They understand black holes not as destructive monsters but as tools, using them for computation and information storage at densities impossible with any other technology. They can create baby universes, new regions of space-time that butt off from ours, perhaps escaping into them when our universe grows cold. They see the full 11-dimensional structure of reality, moving through dimensions we can't perceive, accessing regions of space-time unavailable to beings confined to 3 dimensions. This is science fiction, of course. We have no idea if such things are possible even in principle, let alone in practice. But string theory at least provides a framework for imagining such scenarios, for thinking about what a truly advanced civilization might do with a deep understanding of the fundamental structure of reality. Or perhaps the future is darker. Perhaps string theory is wrong, or correct but forever beyond our ability to test. Perhaps we've reached the limit of what humans can understand about the universe. Perhaps the deeper layers of reality are too complex, too abstract, too far removed from everyday experience for our brains, evolved to hunt and gather on the African savanna, to comprehend. This would be a kind of tragedy, to be intelligent enough to ask the deepest questions about existence but not intelligent enough to answer them. Like dogs trying to understand quantum mechanics, we might be hitting the cognitive ceiling of our species. Future physics might require augmentation, either through artificial intelligence or through biological enhancement of human cognition. But I don't think we're there yet. History is full of people declaring that we've reached the limits of understanding, and history has consistently proven them wrong. Every generation of physicists has encountered phenomena that seemed incomprehensible, and every generation has found ways to comprehend them. Quantum mechanics seemed insane when it was first developed. Relativity violated common sense. Yet we've learned to work with these theories, to build intuitions, to make them tools for understanding nature. String theory is harder, more abstract, more removed from direct experience than anything that came before. But that doesn't mean it's beyond us. It means we have to work harder, think more carefully, develop new mathematical tools and new physical intuitions. The human mind is remarkably flexible. We can learn to think in 10 dimensions, to visualize Calabi-Yau manifolds, to reason about brains and holography and emergent spacetime. Let me tell you about the people who work on string theory, because they're as much a part of the story as the theory itself. They're not all brilliant loners having sudden insights in isolation. Most are part of research groups, collaborating with colleagues, teaching students, attending conferences, writing papers. They're ordinary people in many ways, with families and hobbies and lives outside physics. But they've dedicated their careers to understanding the fundamental structure of reality, often with the knowledge that they may never see experimental confirmation of their work. Some are motivated by pure curiosity, the desire to know how things work at the deepest level. Others are drawn by the beauty of the mathematics, the elegant structures that emerge from the equations. Still others are inspired by the grand vision of unification, the dream of a single theory that explains everything. And some, perhaps, are motivated by a kind of spiritual quest, a search for meaning and purpose in understanding the cosmos. There's a certain courage in dedicating your life to a theory that might be untestable, that might turn out to be wrong, that might be forgotten by history. But there's also a certain faith, not religious faith, but faith that the universe is understandable, that mathematics is a guide to truth, that beauty and elegance are signs we're on the right track. Of course, faith can be misplaced. Beauty has led physicists astray before. Elegant theories have turned out to be wrong. The universe doesn't owe us comprehensibility. But without faith that understanding is possible, science can't proceed. Every scientist has to believe at some level that the effort is worthwhile, that the questions can be answered, even if the answers are difficult and take generations to find. What about you? What drives your curiosity? When you look up at the night sky, do you wonder what the stars are made of, how far away they are, where they came from? Do you ask why there's something rather than nothing, why the universe exists at all? Do you feel a sense of awe at the vastness and complexity of it all? Or does it make you feel small, insignificant, uncomfortable? These are the feelings that drive science, or at least certain kinds of science. The desire to understand, to explain, to make sense of the cosmos. String theory is one answer to those questions. Perhaps the answer, perhaps not. But the questions themselves are timeless, as old as humanity, maybe older. As long as there are minds capable of wonder, there will be people seeking answers. Let me take you to the edge of current research, to the places where string theory blurs into speculation and imagination. Some physicists are exploring connections between string theory and other areas of science. Could the mathematics of string theory describe neural networks or ecosystems? Are there analogs of holography in biology or sociology? It sounds far-fetched, but science has a history of finding unexpected connections. Others are pushing string theory in new mathematical directions, exploring what happens when you relax certain assumptions or generalize certain structures. There's F-theory, an extension of string theory involving 12-dimensional spacetime. There's exceptional field theory, which unifies different versions of string theory into even more abstract frameworks. And then there are the really wild ideas. Some physicists speculate that consciousness might be related to quantum phenomena in the brain, and that string theory might be relevant to understanding those phenomena. Others wonder if the constants of nature might vary slowly over cosmological time, and what that would mean for string theory. Still others explore whether mathematics itself might be different in other universes, whether logic and arithmetic might be contingent rather than necessary. These are ideas at the frontier, barely formed, more questions than answers. But this is how science advances, by asking crazy questions and seeing where they lead. Most of these ideas will turn out to be dead ends. A few might revolutionize our understanding. We won't know until we explore. Now let me bring us back to Earth, to the practical question of what string theory means for you, for your life. In one sense, it doesn't mean much. Whether the fundamental constituents of matter are particles or strings doesn't change the fact that you need to eat and sleep and work and love and find meaning in your existence. The laws of chemistry and biology and psychology work the same way regardless of what's happening at the Planck scale. But in another sense, string theory and physics more broadly can change how you see yourself and your place in the universe. You're not separate from the universe, looking at it from outside. You're part of it, made of the same stuff as stars and planets, governed by the same laws. Every atom in your body was forged in the heart of a dying star. You're literally star stuff, as Carl Sagan famously said. And if string theory is correct, you're even more intimately connected to the cosmos. You're made of vibrating strings, the same fundamental entities that make up everything else. The particles in your body are literally playing their part in the cosmic symphony, vibrating at frequencies that give rise to the quarks and electrons that make up atoms, that make up molecules, that make up cells, that make up you. There's something profound about that realization. It can make you feel small, sure, a tiny pattern of vibrations in an unimaginably vast universe. But it can also make you feel connected, part of something larger, a participant in the fundamental processes that govern reality. let me address some of the criticisms of string theory more directly. One common criticism is that it hasn't made any successful predictions. This isn't quite true. String theory predicted the graviton before anyone was looking for it, though admittedly we still can't detect gravitons. It predicted that black holes have entropy, later confirmed by Hawking's calculations. It predicted supersymmetry, though that hasn't been observed yet. But the deeper criticism is that string theory hasn't made predictions that distinguish it from other theories, predictions that we can test and that would prove string theory right and alternatives wrong. This is fair. Most of string theory's predictions are at energy scales far beyond current experiments, or they're generic predictions that many theories make. Another criticism is that string theory is too flexible, that it can be adjusted to fit almost any observation. With 10 to the 500 possible vacua in the landscape, you can always find one that matches whatever we observe. This makes the theory unfalsifiable, the critics say, and unfalsifiable theories aren't scientific. Defenders of string theory respond that the theory isn't as flexible as critics claim. Most of the landscape consists of vacua that don't look anything like our universe. Finding vacua that even roughly match our observations requires significant fine-tuning, and the Swampland program aims to identify generic predictions that apply across the landscape, predictions that could falsify the entire framework. A third criticism is that string theory has sucked up too many resources, too much talent, too much funding, at the expense of other approaches. This is a valid concern, though it's less true today than it was 20 years ago. The physics community has become more pluralistic, with significant work happening on alternatives like loop quantum gravity, causal dynamical triangulations, asymptotic safety, and other approaches to quantum gravity. These criticisms deserve to be taken seriously. String theory is a work in progress, an unfinished research program. It might be wrong. It might be right but untestable. Or it might be the foundation of the next revolution in physics. We don't know yet, and we might not know for decades or centuries. But here's what we do know. String theory is mathematically consistent, deeply beautiful, and has revealed unexpected connections between different areas of physics and mathematics. It's the only framework we have that unifies gravity with quantum mechanics. It's made contributions to our understanding of black holes, cosmology, nuclear physics, and condensed matter physics. Even if it turns out to be wrong as a theory of nature, it's been enormously valuable as a theoretical tool. Let me take you on one final journey into the heart of what makes string theory so compelling despite all the uncertainties. It's the sense that we're glimpsing something true and deep about reality, even if we can't yet prove it or fully understand it. Throughout the history of physics, there have been moments when the mathematics pointed toward truths that seemed absurd but turned out to be correct. Maxwell's equations predicted electromagnetic waves traveling at the speed of light, which seemed like a coincidence until Einstein realized that light is an electromagnetic wave. Dirac's equation predicted antimatter before anyone had observed it. General Relativity predicted black holes and gravitational waves decades before we had the technology to detect them. Again and again, beautiful mathematics has turned out to describe reality. String theory has that same kind of mathematical beauty. The equations are elegant. The structure is rich and deep. Pieces fit together in ways that seem too perfect to be coincidence. This doesn't prove the theory is correct, but it's suggestive. It makes physicists think they're on to something real. There's also the fact that string theory is unique in certain ways. It's the only known consistent theory of quantum gravity in certain contexts. You can't just modify it arbitrarily. The mathematics constrains what's possible. This rigidity suggests the theory is tapping into something fundamental about how reality must be structured. Imagine you're trying to solve a jigsaw puzzle, and you find a piece that fits perfectly into a corner. You haven't completed the puzzle yet. You don't know what the full picture looks like. But that one piece, fitting so perfectly, suggests you're on the right track. That's how many string theorists feel about their work. They've found pieces that fit together beautifully, and they're working to complete the picture. As we come to the end of this journey through string theory, I want to leave you with some questions to ponder. What does it mean for something to be real? Are the strings of string theory real in the same way that atoms are real, or are they mathematical abstractions that help us organize our thoughts? Is there a difference between those two things? If string theory is correct and our universe is one of 10 to the 500 possibilities, does that change how you value your life, your choices, your relationships? Does it matter that there might be other versions of you in other universes making different choices? What would it mean for human knowledge if string theory turns out to be correct but forever untestable? Would we accept it as truth based on mathematical consistency and elegance alone? Should we? And perhaps most fundamentally, why is there something rather than nothing? String theory doesn't answer this question. It assumes the existence of strings and the laws governing them, but it doesn't explain why those things exist rather than nothing existing at all. Is this a question science can answer, or does it lie forever beyond the reach of empirical investigation? Think about the journey physics has taken us on over the last century. We've discovered that matter is mostly empty space, that particles can be in multiple places at once, that time flows at different rates depending on how fast you're moving, that the universe began in a big bang and is expanding ever faster, that most of the universe is made of dark matter and dark energy that we can't see or touch, that black holes exist and can merge, creating ripples in space-time itself. Each of these discoveries seemed impossible before we made them. Each one expanded our conception of what's real, what's possible, what the universe is like. String theory, if confirmed, would be the next step in that journey. It would tell us that the fundamental constituents of reality are one-dimensional strings. That space has 6 or 7 extra dimensions we can't perceive. That our universe might be a brain floating in higher dimensional space. That there might be 10 to the 500 other universes with different laws of physics. These ideas seem as impossible now as quantum mechanics seemed impossible a century ago. But the universe has a history of being stranger than we imagined. Our intuitions, evolved to navigate a world of medium-sized objects moving at medium speeds, are terrible guides to the very small, the very fast, the very massive. We have to follow the mathematics, the experiments, the observations, wherever they lead, even if they lead to conclusions that seem absurd. This is the adventure of science, and string theory is one of its most ambitious chapters. Whether it's the final chapter or just another step along the way, we don't yet know. But the journey itself, the quest to understand the fundamental nature of reality, is one of the most noble pursuits of the human mind. As you go about your day, as you interact with the world around you, remember that you're experiencing only a tiny slice of reality. There are scales of size and energy and time that you cannot directly perceive. There are dimensions you cannot see. There are phenomena you cannot imagine. The solid world around you is mostly empty space. The particles that make you up are vibrating with quantum uncertainty. And if string theory is correct, at the deepest level, everything is music, vibrations of strings playing out the symphony of existence. Does this fill you with wonder, with terror, with curiosity, with indifference? Your reaction is your own, shaped by your experiences, your personality, your worldview. But I hope this journey has given you a sense of how deep the mystery goes, how much we've learned, and how much we still don't know. The universe is under no obligation to make sense to you. It doesn't care about your intuitions or your comfort. It simply is what it is, following its laws with perfect indifference. But you have the capacity to wonder about it, to ask questions, to seek understanding. That capacity is precious. It's what makes us human. String theory represents the cutting edge of that quest for understanding. It's a work in progress, incomplete, uncertain, possibly wrong. But it's also bold, ambitious, beautiful, and just maybe true. In the coming decades and centuries, as technology advances and our mathematical sophistication grows, we'll learn more. We'll test predictions, refine the theory, perhaps confirm it or perhaps abandon it for something better. But whatever happens, the question string theory asks will remain. What is the fundamental nature of reality? How does gravity fit with quantum mechanics? Why does the universe have the properties it does? These questions have driven physics forward for generations, and they'll continue to drive it forward, regardless of whether string theory provides the answers. You've now glimpsed one of the most profound and ambitious scientific theories ever conceived. You've seen how it attempts to weave together gravity and quantum mechanics, particles and forces, space and time, into a single, unified framework. You've explored extra dimensions, vibrating strings, brains and multiverses, black holes and big bangs. You've confronted questions about the nature of reality, the limits of knowledge, the place of humanity in the cosmos. Where you go from here is up to you. Maybe this has sparked a curiosity that will lead you to learn more, to study physics or mathematics, to pursue your own questions about the universe. Maybe it's just given you a new perspective on your place in the grand scheme of things. Maybe it's left you confused, overwhelmed, or skeptical. All of those reactions are valid. But I hope, at the very least, you've felt a sense of awe. Awe at the complexity and strangeness of reality. Awe at the capacity of the human mind to grapple with such abstract concepts. Awe at the possibility that we might, someday, truly understand the fundamental nature of everything. The universe is vast beyond comprehension, ancient beyond measure, strange beyond imagination. And yet here you are, a pattern of vibrating strings or quantum fields or whatever turns out to be fundamental, capable of contemplating your own existence and the nature of reality itself. That's remarkable. That's worth pondering. String theory may be right or wrong, but the quest it represents, the drive to understand, to explain, to unify our knowledge into coherent frameworks, that quest is eternal. As long as there are minds capable of wonder, there will be people pushing at the boundaries of knowledge, asking how deep the mystery goes, seeking the theory of everything. And perhaps in some distant future, someone will look back on our era and smile at how close we came or how far we were from the truth. Perhaps string theory will be remembered as the moment when humanity finally grasped the fundamental nature of reality. Or perhaps it will be a footnote, an interesting but ultimately incorrect detour on the path to real understanding. We don't know. We can't know, not yet. But we can wonder. We can question. We can explore. We can push the boundaries of human knowledge just a little further, adding our small contribution to the grand project of understanding the cosmos. That's the promise and the challenge of string theory. It offers a glimpse of a unified reality, elegant and mathematical, where everything emerges from vibrating strings in higher dimensions. But it demands patience, faith, and a willingness to venture into realms of abstraction far removed from everyday experience. It asks us to trust the mathematics even when we can't test the predictions, to believe in extra dimensions we can't see, to accept that reality might be far stranger than common sense suggests. Whether you accept that invitation is up to you. But the invitation is there, extended by the universe itself, written in the language of mathematics, waiting for minds brave enough and curious enough to explore what lies beyond the visible, beyond the testable, at the very edge of human understanding. This is string theory. This is the theory of everything. This is our best, most ambitious attempt to answer the deepest questions about existence. It might be right. It might be wrong. But it's undeniably one of the most beautiful, profound, and audacious intellectual achievements in human history. And the story is far from over. The next chapter is being written right now, in universities and research institutes around the world, by physicists exploring new mathematical structures, by experimentalists searching for subtle signatures, by theorists asking what-if questions and following the logic wherever it leads. Perhaps, someday, someone listening to these words will contribute to that next chapter. Perhaps you'll be the one to find the key that unlocks the mysteries string theory presents. Perhaps you'll be the one to confirm the theory or refute it, to complete it or replace it with something better. Or perhaps you'll simply carry with you a sense of wonder, an appreciation for the depth and strangeness of reality, a recognition that the universe is far more mysterious and marvelous than everyday experience suggests. That alone would be a victory, a small step toward a more informed, more curious, more awestruck humanity. The cosmic symphony plays on vibrating strings or quantum fields or whatever constitutes the fundamental fabric of reality, creating stars and planets, atoms and molecules, cells and organisms, thoughts and dreams and consciousness itself. You are part of that symphony, a note in the grand composition, ephemeral but real, small but significant. String theory is our attempt to read the score, to understand the composition, to grasp the underlying structure that gives rise to the music. We haven't finished reading it yet. We may never finish. But the attempt itself, the reaching toward understanding, that's what makes us human, what makes us more than just patterns of matter and energy drifting through space. So look around you with new eyes. The solid world is mostly empty space. The particles are waves. Time flows differently depending on your motion. Space might have hidden dimensions. Reality might be a hologram. And at the deepest level, everything might be strings, vibrating in patterns that create the richness and diversity of all existence. This is the vision string theory offers. Incomplete, uncertain, but breathtaking in its scope and ambition. This is where physics has brought us, to the edge of the known, peering into the unknown, armed with mathematics and imagination and an insatiable curiosity about how things work. The journey continues. The questions remain. The mystery deepens even as our understanding grows. And somewhere, in the mathematics of string theory, in the vibrations of one-dimensional strings in 10-dimensional space, might lie the answer to everything. Or perhaps the answer lies elsewhere, in a framework we haven't yet imagined, waiting for the next Einstein or Hawking or Witten to discover it. Time will tell. The universe will reveal its secrets at its own pace, indifferent to our eagerness, rewarding only our persistence and our willingness to follow evidence wherever it leads. This is string theory, the theory of everything, humanity's most ambitious reach toward ultimate understanding. And this is just the beginning.